So thank you very much for giving me the opportunity to talk to you. And as Sergey was saying, I will talk about symbolic AI, not about machine learning and deep learning AI. Also, I will mention these points very briefly also during my talk. So my talk is about automated reasoning and applying automated reasoning in context which we call nowadays cognitive reasoning. I will divide my talk into three parts. In the first part, I will talk a little bit about history and the nature of automated reasoning, theorem proving. In the second part, I will talk about human reasoning, which is very different from automated reasoning. And in the last part of my talk, I will talk about cognitive reasoning. So let's start with the first part, about a little bit about history. Automated reasoning, so to say, starts in the Age of Enlightenment. In the Age of Enlightenment, philosophers had the idea to understand what's going on in the world. In the Dark Ages and after that, there was the saying, Magister Dixit. That means if the teacher is telling you he's right, don't ask anymore. The teacher is always right, and this is the explanation. The teacher is saying it. Yeah? And this changes in the Age of Enlightenment. People wanted to understand what is in between. Why is it the case? And one of the famous German philosophers, Leibniz, he was depicting a scenario of the future. And his dream of the future was that in the future, philosophers, mathematicians, logicians will not dispute anymore. They will sit on a table and they will say, calculemus, let's calculate. And by calculating, they will solve all problems. This is a fascinating idea, which we still are dreaming of today. So this was the very beginning of, so to say, automated reasoning, of trying to do reasoning in an automative manner. And of course the field of AI, which started in 1956 at the famous Dartmouth conference, has always been a very vivid area of research. But to be honest, it was going up. There were a lot of ups and downs. I mean, in the 1980s, there were the expert systems. In 1996, there was this famous Deep Blue system by IBM, which won in a chess tournament against Kasparov, the world champion in chess. In 2010, IBM came up with the Watson system. The Watson system won the Jeopardy quiz. We will talk about this later on. And nowadays there is AlphaGo, which won against Go, and so on. AI is going up like a rocket nowadays. And very many people are meaning machine learning, deep learning, when they say AI. This is not the case. I mean, in the meantime, there is a kind of a change. Deep learning alone is not enough. Today I read a newspaper article about a project which is run by IBM at MIT in Massachusetts. It's a 240 million project, and they are trying to explain AI. And IBM Watson and MIT researchers are trying to bring symbolic and deep learning AI, statistical AI, together in order to explain what's going on during learning, because this is one of the big drawbacks of deep learning AI. But again, I said it, I will concentrate on automated theorem proving. I mean, back in the 1980s, this was the time when I began thinking about theorem proving. There was a paper which was called 75 Problems for Testing Automated Theorem Provers. Within this paper, the author gave 75 problems for testing theorem provers. And whoever was writing a theorem prover used one of these problems to test his prover and to show how good his prover was. This is one of the problems. Yeah? Given our three equations here. This is the logical formulation of these three equations. And you have to show that these three equations imply this equation. I mean, this is a very, very simple task nowadays. But you see, these were the kind of problems originating from mathematics which we were trying to solve at that time. Yeah? This was in the 1980s. The situation changed dramatically. Nowadays, we are trying to solve problems where we have knowledge bases with more than 500,000 of concepts which form an ontology. And we want to use this ontology within our reasoning process, just like humans are doing reasoning with a huge lot of knowledge in the backhand. In this research psych, which is one of these knowledge bases, we have more than 5 million assertions, facts and rules, more than 26,000 relations, and all this interrelates together, constrain each other, and defines, so to say, the knowledge. And our provers have to deal with this knowledge. Yeah? And there is even an open version of Psych, OpenPsych. It can be downloaded from the net, and even this OpenPsych has more than 3 million of formulae. And you can imagine how clever you design your theorem prover, you will not manage to handle all 3 million of formula efficiently. Remember the examples from the previous slide, 3 equations and 1 formula to be entailed. They're very, very different. And there is, of course, nowadays an increasing interest in applications. I mean, if you do automated reasoning, you have to show that you really can use your system. There is one very important development which helps to solve applications, and these are benchmarks. And in nearly all areas of computer science, nowadays we have benchmark suits where you can test your systems. And for automated deduction, automated reasoning, we again have these benchmarks. And the most famous one is the TPTP benchmark suit. TPTP means thousands of problems of theorem proving. Yeah? And based on this TPTP, there is also a competition, a yearly competition. Now, what's about this TPTP? The important thing of a benchmark is that you have a fixed syntax. Every prover, up to that time, every prover used his own syntax of predicate logic. And of course, if you use a general benchmark, then you have to have a fixed syntax, which is a kind of norm. You have different categories within these benchmarks, and you can concentrate on this category, on this category. You have different level of degrees of difficulty. And what is very important, this benchmark is open. No one can complain with his prover saying, well, but there are only problems which are good for that prover and problems which are good for my prover are not within this benchmark. It is open. Then the administrators of the TPTP would ask him, please submit your problems. We are happy to include it into the benchmarks. Yeah? And there are many, many more extensions. So based on this, we have this CASC system competition, which is a yearly event. And this is really interesting. It's based on the TPTP. And the systems get very robust by this competition because the systems designer have to deliver the system, and it's running from batch. They cannot fiddle in and in between the competition. It's running completely automatically from batch, and it has to be robust in order to run. And the important thing is that you can compare the systems every year. You can see what is the progress of the field. You can see, are there newcomers in the field? How good are they? These newcomers, and this is a kind of an empirical touch which the area gets. Of course, there are some drawbacks also. There are some colleagues which tune your systems. They tune the system to run only on this benchmark suit, and they do not embed the systems into applications. Yeah? And also, they are not interested in the proof result. They are interested only in solving a problem, but you don't get an explanation out of it why you solved the problem. These are some drawbacks about this CASC. Let me give you a very brief idea how different theorems prover might work. For this, I have a very small example, a small knowledge base. So we have some systems. If a system S is here, there may be 2 courses, course C1 or course C2. For course C1, there is a treatment T0. For course C1, there is a treatment T1, so you have 2 possible treatments for in case of C1. For C2, you also have 2 possible treatments, T0, T2. So very small and tiny knowledge base, which we use now for theorem proving. Before we use this formula, we usually transform it into closed normal form. This is a kind of syntactic transformation which preserves correctness or satisfiability, however you put it. But this is a syntactic transformation in order that our system can get used with these formulas more efficiently. So we start with this closed set, right? So we have mainly three different kinds of theorem proving. The first one is goal-oriented. So again, we start with these clauses here. We have a goal, and that goal says there is a treatment. For some technical reasons, we have to negate it because we will shows the unsatisfiability. So the goal is there is a treatment. We don't know the treatment X. We want to learn about that. So for goal-oriented theorem proving, we start with the goal, and then we apply a single inference rule. It's a resolution inference rule. Is anyone familiar with a resolution inference rule for logic? Okay. So, okay, that's enough. I mean, for the others who are not aware of that, it's one rule which takes a formula, a clause, and two formulas, two clauses, and it derives a new one. Let me take this example. We have here treatment. Now, we use treatment of X, C1. We use this clause here and this clause, and we derive this clause, not cos C1. This was one inference step. Now we have another rule, namely we have cos C1. Cos C1, no, I'm lost. Yes, cos C1 is here also. So we use another inference step deriving cos C2 and not symptom S, you see? And we are always working in a linear way. Yeah? It's goal directed. We start with the goal and we continue applying simple inference rules until we get this empty clause, which says our formula is unsatisfiable. We have done, right? You don't have to be curious about the fine-grained detail of this, just one inference, but we start with the goal, working towards the end. And this is a paradigm which people have been using in logic programming. Yeah? In Prolog nowadays it's answer set programming, but logic programming means you have a goal and you go on in a linear way until you proved everything. Yeah? And in the 80s people were thinking that this is the right way to do it. This is the most efficient way to do it because you start with the goal. But, linear deduction, logic probing, answer extraction, I said this. Another approach is a saturation-based approach. Again, we have this closed set, and now we are not starting with the goal. We have a goal, but we don't necessarily start with this goal. We just take some, in an arbitrary way, two clauses out of it, add the resolvents. Take another two clauses, add the resolvent, without any plan, right? Just try to. Should I stay on the other side? A little bit better, yeah. Okay. So we are just trying to apply our inference rule in an arbitrary manner, and we try to saturate the initially given set of clauses without any plan, without any order, and we do this until we derive the empty clause as before. So there is of course a problem because by deriving new clauses in an arbitrary way, there are many redundant clauses, whatever that means. You have to control this saturation, and this was a very good trick people came up in the 90s. They defined orderings on these clauses, and you were not allowed to use arbitrary clauses for new deriving ones, but you have to follow these orderings. And it showed up that these orderings retain completeness and correctness of the inference system, and by this they were very efficient. And also they were very it's very easy to handle equality with that, and it was easy to combine all this with decision provers. Nowadays, the most efficient provers around are all saturation-based provers. I will show you an example in a second. And the third method I want to talk about is a tableau system. Tableau systems are a completely different branch. it's not saturation, it's not goal derived. In Tableau systems, you have a proof object. In saturation-based systems, you had a set of clauses. Here you have one object you're working on. You see, this is a kind of a tree. And you try to construct this tree out of these clauses. I will not go into the rules how to construct this tree. But anyway, you can always work on this data structure. And you have a data structure at hand. And if you succeed and you find a proof, then you know exactly why you found this proof. Yeah? You get an explanation because this passes in the tree. They correspond somehow to the models of the initial formula, if there exists a model. And this Tableau systems are insofar very well suited for applications because you have a really single proof object you're working on. You generate model, and you even can do common sense reasoning by adding minimal models. One problem with these Tableau systems, for various technical reasons, I don't want to mention that, was always equality, but even this was solved by some of my colleagues and myself in the beginning of 2000, so that we could handle equality very efficiently also in this hypertableau. I'm a fan of these hypertableau systems because in my applications, and we will see it in half an hour or so, that these hypertableau have some properties which are very well suited for applications. Okay, so this is the result of this year's competition, which was 2 years ago, 2 weeks ago in Brazil at the conference on automatic deduction. You can see we have these different divisions. This is a division on higher order theorem proving. This is in typed order. This is first order theorem proof. It's the most prestigious division. And you can see here, this is Vampire. He's a winner. This is the new version. This is the last year's version. He's still the leading system. He's a saturation-based prover. E is also a saturation-based prover. This one is interesting. No, this one here, sorry. This one is a propositional theorem prover with augmented by theories. So this is very interesting that these kind of provers are also competitive. And this is the only Tableau prover in here, LeanCop. Yeah? So you can see the winners are saturation-based theorem provers. I wouldn't have expected that in the 1980s, in the 1990s, that these are the winners, so to say. Okay, so this was a very brief overview on automated deduction, automated theorem proving. Now let's focus a little bit more in applying it. So this is one example from the TPTP, from this benchmark, from the division of puzzles. This is the simplest examples. This is the way this benchmark is organized. You have a description of the problem. You have some statistics, how many unit formulae, how many equalities, and so on and so forth. Now let's have and of course you have the form. You have given the problem in predicate logic. But let's have a look to this description of the puzzle. I mean, this is a description with saying someone lives in a mansion and someone killed Aunt Agatha. Agatha, the butler, and Charles live in Dreadmore Mansion. I mean, you know these riddles, and you have to find out at the very end that Agatha killed herself. I mean, it's a very easy examples. You can take this example, transform it into predicate logic, and then you give it to a theorem prover. So this is a transformation into predicate logic. I mean, it's a strange syntax, but you see that means that means who hates Agatha also hates the butler, or this means no one richer than Agatha hates the butler, or this means Agatha is not the same person as the butler, and this is the conjecture you have to prove. Agatha killed herself, right? A very simple problem once you transform it into predicate logic, and if you put it into your prover, it runs immediately in 0 seconds. You get the message proved, Agatha killed herself. So, but let's have a software engineer's view to this problem. This was the natural language description here. I gave it to a human, he thought about that, and then he transformed it into a set of clauses, right? You saw that. And this set of clauses was fed into the theorem prover, which gives you immediately yes. Yeah? But the main task, transforming these sentences into logic, was done by a human. That means he has to understand the natural language, he has to formalize the riddle, the puzzle, and then we could give it into the prover. If we want to do that automatically, we have to feed in the natural language sentences into a system. The system would produce a clause set, and we would try to give this clause set to our prover. So for this machinery, we use a system by Johan Boos, a linguist from the Netherlands. The system is described in this paper here, and this is a so-called Boxer system, and it's available via internet. You can try it, and there is an API also for this Boxer system. The Boxer system takes natural language input and produces the semantics of the language of the sentences in predicate logic. This is the result if we fit in our puzzle. I mean, it's completely unreadable, of course. But you might notice that there is more contained in this formula than the riddle stuff. For example, let me see. There is here we have a name agent. There is something like an agent, yeah. Or we have some linguistic information. We have linguistic information saying. It's too small. This is a noun here, N1 people, so this means there's a noun, there are verbs, and so on. This is the semantics of the sentences in natural language as Boxer is understanding it. And now we're feeding this first order formula into our prover, and what happens? Nothing. No proof found. Yeah? And that's the problem, because there is not just the problem extracted in the formula, there is all this linguistic context, and you cannot really prove on the basis of this formula this very, very simple problem, which we could do immediately once a human has transformed it. Now that's a problem if you do the entire chain automatically. Why is this important? Because now I want to go into the area of cognitive computing, cognitive reasoning. And you might have heard about this IBM Watson thing and Jeopardy. Who knows Jeopardy and Watson? Some of you. Okay, great. So, I mean, in Jeopardy, the questions are given in natural language, right? You have to process the natural language problem. The system, IBM Watson system, had a big knowledge base behind him. It was not connected to the internet, so he has to do all locally. And he had to understand the sentence, and then he had to generate the answer. Do you know the answer? In 2002, Eminem signed this rapper to a 7-figure deal, obviously worth a lot more than his name implies. Who is it? What? 50 cents, okay. But you see, that's a tricky question. I mean, I was not aware of 50 cents. I couldn't have solved it. But you have to understand the text in order to see that 50 cents. So this is another question which... I'm sorry, but I cannot enlarge the wall. Okay, so you see, it's tricky. You have to understand the question. You have to acquire your knowledge, and then you have to be fast because the other guys are not sleeping there. Yeah, so this is all done by Watson, right? So, and the interesting thing is that IBM, just in contrast to the chess success in the 90s, this time they changed this success into a business model. They termed the term cognitive computing, yeah, and that's new. Cognitive computing is a paradigm for solving problems, and they call it Watson solutions. There are various parts of Watson available over the IBM cloud and so on and so forth. There was even a chef, an automatic chef, composing new dishes. I tried one of these soups, which was composed by Watson. A delicious gazpacho, was very good. I mean, it's also a good chef. And the point is I was telling you before that IBM and the Watson, IBM and MIT are doing this joint venture research project, and they use Watson and the knowledge from MIT in order to generate explainable AI models. No, cognitive computing, that's the term coined by IBM. What are the characteristics? We have multiple knowledge formats. I mean, Watson were using ontologies, formal ontologies, was using text, natural language text, was using pictures, was using databases. And all these multiple formats have to be combined. And of course, then you need multiple reasoning mechanisms in order to deal with this multiple format. They have to cooperate, let these models cooperate, and of course it's time critical, and of course you should interact with humans, because this is the idea of cognitive computing, that you have a cooperation between machine and humans, and you really should communicate with each other. And this is, for example, completely impossible if you use deep learning only. You cannot communicate about why it is a cat. The deep learning system is telling you it's a cat, I'm sure it's a cat. And you ask, why is it a cat? I don't know, but I'm sure it's a cat. So this would be the dialogue you had with the deep learning system. And of course, with the symbolic AI system, you could communicate. It should tell you, well, because it's a fur, it has whiskers, it has a tail, and so on and so forth. Yeah? Okay, so cognitive computing. But now let's switch a bit more to cognitive reasoning. I mean, this is my concern. I want to learn from humans how they do the reasoning. And this is a very famous experiment designed by Peter Wason, a psychologist, 1962. It's a Wason selection task. Who ever heard about that? No? Yeah? Who had heard about it? There are some more or less, so I can tell you. Okay. So. So those who know the story, please don't answer. So in front of you, there are 4 cards on a table in front of you. The cards are such that on one side there is a letter on every card. There's a letter on one side, and on the other side there is a number. And now the cards are laying in front of you in an arbitrarily switched manner, such that you have 2 letters here and 2 numbers. And now I am stating the rule. If there is a vowel on one side, the opposite side should contain an even number. If there's a vowel on one side, the opposite side contains an even number. You have to check whether I'm right or wrong. You can check this, of course, by switching the cards. And now you are asked, what is the minimal number? Which cards do you have to switch minimally in order to prove that I'm right or wrong? What is your guess? 2? 1? 1? There's no 1. You mean A? You want to check A and 2?
No,
A and? A and N? A and 2, A and N, A and 5? More? More? A?
N minus 1.
N and this one? Or? Okay. So obviously we don't agree. We have very different opinions. So in the original experiment, you had to leave the room now, and there's another group coming in. Assume you are the other group now, and we do the other part of the experiment. Forget what you have seen. So this is a new experiment now. In front of you, there are 4 cards. One side of the card contains a beverage. The other side contains an age. And I don't know how it is in Russia. Which age are you allowed to drink alcohol? 18. So in US it's 21. So let's do the US play. So one card represents a person drinking. This person drinks Coke. On the other side is the age, and so on. So now the rule is, in the US, if a person is under 21 years old, it is not allowed to drink beer. So which person do you have to check whether it obeys the rule? Which one? This one? In order to check whether it's drinking beer, and this one. Very easy, right? It's very obvious. But it's exactly the same problem, right? I mean, if, then, if, then. Yeah? In this case, only 25% of all people gives the correct answer, which is now, what is the correct answer?
A and 2.
A and 5, exactly. I mean, if this is no vowel, so I don't care what's on the other side. This is an even number. I don't care what's on the other side, because if it's a vowel, it's fine. If it's a... okay. I mean, I had to convince you now. In the same experiment here, I had not to convince you. You believe me immediately. And this is the interesting thing. And we know nowadays, I mean, 75% of all persons give the correct answer in this case. And we know nowadays that these are different parts of the brain which are solving this problem. Because this problem has to do with social contracts. And social contracts are solved in the brain. So detecting cheating in social contracts are solved in the brain by this part which is responsible for emotions, for emotion recognition, for example, in the face, because it's a very, very old problem in the evolution of mankind to see whether someone is angry or not, whether someone is fulfilling a social contract or not. This is done not by not by reasoning, like in the case of the abstract Wesen task, where you don't have a social contract. You just have vowel numbers, and this is an abstract version, and people don't know how to do it. But this they can do very, very efficiently. And the question is, how can we learn from these kind of problems, from this kind of solutions people are using? Another example is the following. 75. To the abstract, 25 more. 25, 30. And even logicians. I did the experiment in my logic courses, in my AI courses, and in conferences where logicians were attending. They do, and every logician knows the implication. That's the same, not A or B. A implies B. But if you have to apply it, it's much more difficult. Now, another example where humans are doing strange things. So this is an implication. If she has an essay to write, that's propositional logic, very easy. If she has an essay to write, she studies late, right? This is a fact. She has an essay to write, and now I ask you, is it the case that these two formulas imply that she studies late? This is obviously the case, right? I mean, this follows logically from these two statements. So now let's add a third statement. 98% of all probants are doing this correctly. Yeah? Very easy task. Now let's add another statement. If she has a textbook to read, she studies late. So now we have these three formulas, and we ask again, is she studying late? Yes, nothing changed. I mean, she has an essay to write, and I mean, this has to do nothing with the textbook, right? So she studies late. Now let's change things a little bit. I mean, this is the reason why this is a disjunction. Forget it. So let's change a little bit. Now we add another formula. If the library is open, she studies late. And now I ask again, is it the case that she is studying late? I mean, seeing it logically, it's of course the same case. I mean, it's exactly the same. But most people are not so sure about it. Now they start thinking. They start thinking, well, what about the library? I mean, if it's if it's not open, and now the correctness rate is dropping dramatically. It's dropping to 38% from 98 to 38%. Yeah. What do you guess is the reason for that? I mean, there are psychological theories. So it is Ruth Byron, which does this kind of experiment. She's in Great Britain, a cognitive scientist. What do you think could be the reason why people are performing so bad in these cases?
I think it's a conjunction of premises.
Yeah, but look, if usually in my logic classes I would go to the blackboard. We have no time for that. I would rewrite this. Instead of acid to write, I would write P implies Q, R implies S. And this is logically completely sound. I mean, I can change names, right? I can change symbols in logic as long as I do it consistently. So you look to these symbols now, to these symbols, and you immediately assign a meaning to it. I mean, you assign library open. If the library is closed, I cannot stay in the library. If there would be a P or a Q, you wouldn't have assigned this meaning. And then you start thinking. So when people do reasoning, they are doing not abstract reasoning. These names are important. And I will come to that in 10 minutes later, that these names are important, although logically these names are completely unimportant. So this is how humans are doing reasoning. Yeah? This is the so-called suppression task. And there are many, many more experiments about that. So what was I telling about humans? Because in the meantime, there's a growing interest in common sense reasoning benchmarks. You know, common sense reasoning is this kind of reasoning which is here depicted. All birds are flying. Tweety is a bird. Is Tweety flying? Yes, of course. But Tweety is a penguin. No, it's not flying. You see? I mean, this is a kind of a common sense reasoning. And people in common sense reasoning very often use these kind of toy examples in their papers. And this changed dramatically. Nowadays, they are introducing benchmarks, as I told you before in the TP-TP case of first order proving. Here, the common sense reasoning people introduce benchmarks as well. And I want to focus now in the rest of this talk to these benchmarks. Let's skip that here, because it's no video anyway. Let's skip that. So, this is these are two examples from two typical benchmark sets. The one is the so-called Vinograd Schemas Challenge, which was introduced by Hector Levesque in 2011, and there are competitions about that. And this is an example here. You get a sentence in natural language, and then you ask a question. The sentence is: the trophy wouldn't fit in the brown suitcase because it was too big. Now, the question is, what was too big? You have two alternatives, the trophy or the suitcase. I mean, it's very obvious. It's it's a suitcase, because you know that the suitcase is a container and it contains object, and the object has to fit into the container, and if it's too large it does not fit, and so on and so forth. There's a lot of knowledge involved in solving this very, very simple question. The other one, Romiley et al., also 2011, choice of plausible alternatives. This is a very nice author. The man broke his toe. What was the cause for this? There are two alternatives. He got a hole in his sock, or he dropped the hammer on his foot. And of course you know that it's not the hammer, that it's not the hole in the sock, yeah? Because, and so on and so forth. So, and this kind of problems has to be solved automatically. So the system has to translate the natural language into internal logical representation, and then it has to do the reasoning. And this is what we are doing, and I will explain this a little bit to you. So there are two, I mean, we start with semantics, we start with natural language. There are two, in principle, two different ways to represent the semantics of natural language. One is map a given sentence into a meta language, say logic. There are a lot of logics, Montague grammars and higher order logics, which are used by linguists to represent the meaning of a given sentence. The system from Johann Bose is doing exactly this. It takes a sentence and it maps the sentence in logic, and I showed you this before. The other kind of semantics is so-called distributed semantics. It goes back to the linguist Joseph Firth in 1957, and it can be characterized by his saying a word is characterized by the company it keeps. And this is more or less the way a child is learning semantics of language. I mean, a child does not map a sentence in predicate logic or in whatever. A child, notice that if you have tree and leaf, then these words are close to each other. If you have tree and wood, they are close to each other. If you have tree and brick, they are much far away from each other. Yeah? So this is what First is trying to say. A word is characterized by the company it keeps in a given corpus, in a given sentence. And this is a second way to characterize semantics. We will use both, but for the moment we stick to that one. And as we did it before, we take one of these problems. This is a running example now. My body cast a shadow over the grass. The question is, what was the reason for it? There were two reasons, two alternatives. The sun was rising or the grass was cut. So we fit this into Boxer. We get this formula as I showed it to you before. And now we are trying to work on this formula. And this seems pretty easy. Yeah? I mean, it's a small problem, a small formula. This is what our provers should do, be able to do immediately. So again, this is the situation. We have the first order representation of the problem. This is the formula I just showed you, this one. Yeah? So we have this representation here, and we have some background knowledge. Of course, I have to know something about a shadow, about the sun, and so on and so forth. And there are, as I noticed, I gave you an example at the very beginning. There is, for example, OpenPsych, which is this. Battery is empty. OpenPsych, which contains some background knowledge which we are trying to use in order to solve things. Yeah. So, but the problem is, no, this is, maybe, no, here we go. But the problem is that there is a huge gap between the background knowledge and our problem. Why? Why is there a gap? Look, we have here in the sentence, my body cast a shadow. To cast is a verb. Now, the logical representation of this sentence contains the predicate verb cast. In our background knowledge, there is nothing about to cast, but luckily there is something about to project. But how do we know that to cast and to project are related, are synonyms in fact? How can we solve this problem?
Neighborhood of shadow?
Yes, so, but then we would need some word embeddings. We haven't got this yet. For the moment being, I have no distributed semantic. We have just the logic, and here we have also logic, but they don't fit together. But luckily, we can check this by using Wordnet. Wordnet is a huge database, freely available. You can type in words and you get synonyms, you get antonyms, you get a lot out of this Wordnet. Now, if we search for, there's an AP, of course, for Wordnet. If we type in to cast, then we get cast, then we get it's a noun and it's a verb, and there is a synonym for this verb, namely to project. And this is exactly what we want. That is, we use Wordnet via an API in order to bridge this gap in between the background knowledge and the knowledge. Yeah? So, and to bridging this gap means we introduce a new formula, namely cast is equivalent to project for all x. And this bridging equivalence we add to our first order representation, and then we get the following here. We get the first order representation, we get the bridging formula, and we have the background knowledge. And now it seems so as if we are ready to prove. It seems so, but this background knowledge is too large. We cannot feed this into our prover and then search for a proof. Impossible. So we have to find these parts of the background knowledge which are necessary in order to prove that. And that's a tricky thing. And there are some methods around. One is called Sine, and I will come to that in a second or in a minute. How this can be used to select this background knowledge is from the huge given background knowledge in order to prove the problem. Yeah? So, and this selected background knowledge will then fit into our set of formulae. So, and then we start proving. This is our prover, our hypertableau prover. He gets the selected background knowledge with that, and then he delivers one proof object. You remember, when I showed you the different kinds of theorem proving, we had goal-directedness, saturation-based, and the tableau thing. And my argument was, in tableau we have one proof object which can be helpful at the end of the proof to read the reasons, or if we don't get a proof, at least we have a partial proof object. And in fact, this happens here in our problem. This happens that we never get a proof. And the reason for that is that the Boxer formula, I showed you this at the very beginning with und Agatha, this Boxer formula are containing not only the problem but many, many more. So in fact we don't get a proof, but we have to stop after a timeout. So we get a partial proof. And now we get two partial proofs, one for this reason, one for that reason, and now we have to compare these partial proofs, which is better. I mean, this is from a logic's viewpoint completely ridiculous. We have a big machinery, and then we are trying to prove things, and we get timeouts all the time. But we try to make the best out of it. We take these two proofs, and we feed this into a machine learning system which we have trained beforehand in order to find out which alternative was better. Yeah? Which is closer to a logical consequence A or B. This is one point where machine learning creeps into the symbolic reasoning mechanisms in a very proper and in a very sound way. This is what we are trying right now. To improve all that in order to get good numbers on the benchmarks I showed you, because benchmarks are thought to compare systems, which one is better than another one. Now, let's come to the last point, for the next 5 minutes. How can we select this relevant formulae? I mean, we are here, exactly at this point. How can we select these relevant parts with this scene here? And there are two methods for that. So the first one is a so-called syntactical one. This is our knowledge base here. We have some beverages. Beverages are liquids. Beer is a beverage. Chair is a furniture. And we have a definition of the subclass here. If X and Y, if X is a subclass of Y and Y is a subclass of Z, then so transitivity of subclass is defined here. So now let's see how can we use a syntactic criterion to select axioms in order which are necessary for the proof. For this we need the notion of occurrences. So if we have a symbol S like beverage, then occurrences of S is the number of axioms in which this symbol occurs. So, for example, beverage occurs in two axioms, in this one and in this one, right? In these two. Liquid, beer, chair, and furniture is only occurring in one axiom, namely liquid here, furniture here, chair here, and so on. So subclass is occurring in 4 different axioms. Yeah. So and now we can use this number of occurrences to select axioms. And the idea is we have a trigger relation, and this trigger relation defines if a symbol triggers an axiom. If we have a symbol F, we say S triggers an axiom. If all other symbols in the axiom, the occurrences is larger. That means S triggers an axiom, it is very rarely present. The idea is very obvious. A symbol in an axiom which is contained only very few axioms is more important for this axiom than subclass, for example, which is in every axiom. Yeah? A very simple syntactic argument in order to select axioms which are helpful for your proof. So with this huge background knowledge, we can do exactly this one. Yeah, I mean, you can pre-compute a lot. You can have dependencies graphs. You don't have to do it during runtime. You do it beforehand, before your proof. You can compute all these occurrences on your knowledge base, and then you can use these numbers in order to select these symbols based on the syntactic occurrences. This is one method. It's called the Sine method. Come on. This is technical stuff. Let's skip that. we use it. And the second method we are using, in addition to the syntactic, is now this word embedding, which you were proposing beforehand. What is a word embedding? You have a huge corpus, a given corpus. Maybe it's a newspaper article or blog archives or Wikipedia text, which is contracted from a Wikipedia. And then you count within this huge corpus which words are occurring close to each other. Yeah? How often? And then you get a kind of a relationship, a neighborhood measure. For example, is here woman much closer to man than to heiresses, or here brother is closer to sister than to madam here. You see, you get a kind of a landscape of relationships of words, yeah, of similar words. And these word embeddings are available nowadays very easily. You can have word embeddings from huge corpuses. They are available for free. We use number batches, which is one of these word embeddings. And of course, you can compute your own word embeddings. If you have your own corpus, you can use your own corpus for computing the word embeddings. By the way, this is distributed semantics, and this is how these modern translation systems are working. Google Translate, or what you have your own translate system here, are using huge corpuses. Then they are, so to say, computing this word embedding, this similarity measures, and then they are doing the translation based on this kind of semantics. And there's a nice story. I mean, Google Translate has a lot of manpower put in their system. And there's a small company in Germany, it's called DeepL. And this company provably is much better, delivers much better translation quality than Google does. And people were wondering, how is this possible that this small, very small company is better than Google? And it turned out they had a different corpus. They took a corpus from the European Parliament, because in the European Parliament every document has to be translated in many languages, and this is done by high quality translators. Yeah? And this corpus is very high quality corpus, and this is why the similarity measures are much better, and so the quality is better as if you take blog archives where people are translating very weird and so on and so forth. So the corpus quality is very important for this. We'll see that on the example in a second. Now, how can we use this word embeddings to select background knowledge? I mean, this is here again for our example here with the beverages and the beer, and this is are these axioms are triggered by syntactical aspects based on these occurrences, right? Of the occurrences of these symbols. Now, if we want to use a similarity measure, we go through these symbols and allow similar symbols to trigger an axiom as well. So, for example, for beverage, we go to number batch. Number batch is one of these word embedding, and we get some similar words out of it. For example, these are the 100 words most similar to beverages in number batch. For example, a Red Bull here has a similarity distance of 0.9 to beverage. Yeah? Here, beer only 0.7. You can imagine that this is a reason that the corpus was not written by Bavarians or Russians or so. I mean, the corpus is defining that. Red Bull is closer to beverage than beer. This is, for me at least, strange. Yeah? Anyway, so we can use these word embeddings now to get similar things. So we get lager, ale, pilsner, lager. We get all this from the similarity measures from word embedding. And this one we are using as well. And this is what we call similarity scene. It's a new paper. We just introduced it 2 weeks before in the CADE conference in Brazil. And these are the results here. So our proof are hyper on some of the problems here. And if there is a proof, you can see that similarity scene solves much more examples than syntactic scene. That means it pays really off to get this statistical knowledge, a similarity knowledge into the game. This is another story here. I don't want to comment on that. And now we had to, of course, we had to prove that this is not only the case with our prover, then it's a method which is behind, and this is a prover E, which is one of the winners of the CAS competition I showed you before, and it is the same. I mean, if they are proofs, E could prove much more examples with similarity seen here. So that shows, this example shows you that one of the big problems in doing symbolic reasoning in common sense reasoning based on natural language problems is the background knowledge. Humans are very well able to deal with a huge set of background knowledge, and machines have a lot of problems in dealing with that. Machines have a lot of problems in dealing with this. Is just to conclude. We are arguing that it is worth doing symbolic logical reasoning in applications because you get a lot of information as an explanation for your solution. It is worth doing learning from human reasoning. How do humans solve some problems so efficiently? And finally, I wanted to point out that it is worth to combine machine learning and symbolic logic in order to reach explainable AI. Coming back to these benchmarks, the situation with the common sense reasoning benchmarks with the Winograd challenge is in the moment so that the best systems based on machine learning, on deep learning, can solve up to 80% of the problems. But they can say yes or no, this is the solution, but they cannot give you any explanations. Our systems are much worse at the moment being. They are about 60% or so, but they can explain what's going on. And we have to work further to bring these two approaches, deep learning and symbolic logical based AI together in order to get explainable AI. And this is what I wanted to conclude. I'm happy to answer questions. Thank you.
So your theorem prover is more advanced than propositional logic because you deal with quantifiers?
Yes, yes, of course. I haven't noticed that. Propositional logic is decidable, right?
Yes, yes.
Yeah, and we are doing first order logic.
Yeah, but my question is, see I correctly that all statements have at most one, it was too fast to read.
Yeah.
The statements have one quantifier, so there are no with two nested quantifiers.
No, they are nested. You remember I was mentioning at the beginning that we take a formula and we transform the formula into a closed normal form. And this transformation throws away all quantifiers. But the problem is, to be honest, it's not equivalence preserving because of the existential quantifier. But it is non-satisfiability preserving. So for our purposes, it's okay.
And just curiosity, what's the maximal depth of quantifiers?
Arbitrary. I mean, finite but arbitrary.
So it can be large.
It can be large, yes. I mean,
Boxer generates like 5 nested quantifiers.
yes. The problem is, of course, if you have nested quantifiers, then you have to introduce new function symbols for every dependency, existential universal quantifier, and you get new function symbol. And even at the beginning, if you have no function symbol in your problem, so that means you have a finite domain. But the transformation brings in function symbols, and then you get an infinite domain. But that's a technical aspect.
And then I wonder how you can get functions out of the knowledge base. It seems like something.
No, the knowledge bases, these are the predicates. These are predicates. The knowledge base usually does not contain function symbols. You must distinguish between predicate and function symbol. And the knowledge base is usually an ontology without function symbols, right?
Do you use first order logic only or some model logic?
Thank you. Good. Thank you for the question. So I give another talk now. That's interesting because Description logic people, description logic is a logic which is well suited for knowledge representation. I mean, this is an important stuff. But description logic is decidable, should be decidable, because you want to solve your problem in finite time. If we restrict our prover a little bit, then we can handle SHIC, which is a description logic language, and we can decide SHIC. That means the prover is able to do first order logic, but also model logic. Yeah? So it's a switch to.
I have a question. When you translating from natural language to logic using Boxer, why don't you throw away linguistic information after the translation?
Yeah, but what is the linguistic stuff? I mean, I get this formula, this huge formula out. How can I find these parts of the formula which are important? I don't know. I mean, because I throw away the language, the natural language, because I don't understand the natural language. I work on the formula. Yeah. Yeah, if I could do that, this would be a solution. Yes?
Well, I think it's a big deal to convert some statements from the natural language to some formal logic, and it's because of ambiguity of the natural language, I guess.
Yes.
Can we just give up and use some more formal language,
Sure.
languages? For example, if we use Esperanto instead
Yes,
of
yes.
English, would it simplify the problem?
Yes, yes, definitely. I mean, there is work on using a language in between natural language and logic. In logic programming, there is a long tradition on that. Yeah, but of course, I want to do common sense reasoning, and people are dealing with natural language. Yeah? That's the point. I mean, the point is we want the system to communicate with humans, and we don't want the humans to change the way they communicate. You want your Alexa or Siri. Do you want to learn a new language in order to communicate with Alexa?
The English is prerequisite for doing science. Why not that language is to be a prerequisite for doing some proving?
Yeah. I remember the first days when I had a PDA, personal digital agent. So we had to learn new letters in order to. I learned this. You remember? Okay. I was very good in that, but anyway, it's crazy. And nowadays, no one is learning a new writing for putting it into your PDA.
But anyway, so there are two different,
maybe
separate problems. So one is to make the prover to improve, and another to make it for common use.
Yeah.
So they could be separated. So that one should not block the development of this.
Okay. Yeah, I see. But the other way around, our aim was to solve these benchmarks, and they are given in natural language. And before I had another project, I didn't mention that, we had another project where we had to deal with natural language also.
Disambiguation needs large corpuses. This is not included in the...
This is
not a part of the benchmark.
No.
You have to solve the problem without
the disambiguation has to be done in the Boxer part. I mean, when Boxer is translating it, it has to deal with. Boxer is doing this automatically. I don't know how correct he is doing it. I'm not a linguist, so we are just using system out of the box. And
When you translate problem from the natural language to the formal language, you have a kind of voluntary, so you can translate in one way or another.
Yeah.
Yes, but so we can mark our translation with some kind of weights.
Yeah.
This or that, but after formal expression is done, you proceeded with a formal logic with categorical values true or false, and you forgot about uncertainty, which is how to use these fuzzy information from the begin to the end, how to propagate it.
So, if I understood this correctly, you mean from the linguistic analysis, I could have different meanings, and I could use all different meanings alternatively to check this. Yeah, would be, but of course I cannot change the linguistic component, and this was not my goal. So, but you're right. If I had a boxer system which gives me different alternatives as meaning, I could use that. Yeah, I haven't thought about that. Thank you.
Maybe some kind of fuzzy logic. Or quantum calculation.
Yeah.
It's a new layer of complexity.
Yeah. Exactly. This is why I would be very anxious about it. Yeah.
Let's thank Professor Furbach.
Thank you.